Hello and welcome to this edition of the Gen Z tutorial video series. This is one of a series of videos that will introduce Gen Z, what it is, what problems does it solve, and what are some of its high-level attributes and capabilities that make it a powerful solution for next-generation infrastructure. This video series is made in three parts. Gen Z, a new approach, introduces the challenges faced by today's infrastructure and why Gen Z offers an opportunity to drive new levels of innovation. The Gen Z tenets provides a list of the architectural tenets that drove the design, protocol definition, and specification of Gen Z. And finally, there are a series of videos for a number of Gen Z use cases, which are examples of how to apply Gen Z technology into various real-world infrastructure components and solutions. Today we present the Gen Z DRAM and storage class memory use case. Let's begin. This module describes some of the key aspects of applying Gen Z technology to DRAM and storage class memory, or SCM, components, as well as the host components that these memory components will be connected to, such as CPUs, GPUs, SoCs, etc. We will look at the ways Gen Z-enabled memory components allow us to build a new class of infrastructure better suited to tackle next-generation workloads and applications. Unlike today's memory interconnects, Gen Z truly is a universal memory interconnect. Let's take a look at how Gen Z can be used for memory interconnect between a CPU, for example, and memory components of various types and generations. We'll begin by looking at how memory interconnect is implemented today. In the figure on the top left, we see a DRAM DIMM connected to a CPU, processor, SoC, or other host component. Let's just call it a system on a chip, or SoC for now. The SoC has both an integrated memory controller for memory operations with external memory, and the media controller logic block that actually understands the DDR bus interface and protocol, which is native to synchronous double data rate, or DDR, DRAM memory. Since the media controller is integrated into the SoC, this means that the SoC and external memory module are forced into lockstep as far as technology evolution are concerned. In addition, this limits the types of memory that can be supported by the SoC at any point in time. These limitations are illustrated in the animated figure on the upper right. The SoC and memory must progress over the course of time in technological lockstep, from generation to generation. This limits innovation and system flexibility, making it difficult to quickly adapt to changing workloads and market requirements. In addition, the memory types that can be supported by the SoC are baked in when its design is completed. Thus, it cannot support different types of media that are introduced after the SoC's design cycle is completed. Again, this severely limits innovation. Now, let's take a look at how Gen Z can help alleviate these limitations. Watch the animation carefully on the left as we transform the static memory interconnect into a dynamic universal memory interconnect. This is an animation that depicts the fundamental architectural change where the media controller is migrated from being integrated into the SoC to be integrated into the memory module itself. A Gen Z logic block is added to both the SoC and the media controller to allow a memory-agnostic asynchronous protocol to facilitate high-performance memory accesses from the SoC to the memory module. This change allows us to do two things. First, we unlock the lockstep innovation between the SoC and memory module. And the SoCs and the memory can evolve completely independently of each other. Second, we can now support a wide range of memory technologies, which is especially important for storage class memories, where there are many variants with different attributes that may be required for different workloads. Thus, an SoC can support memory generations and types not comprehended in the original design of the SoC. This capability enables a new level of innovation for memory and host component development. Let's take a few moments to look at the evolution of host components, CPUs, GPUs, etc., and their journey towards Gen Z adoption and the effects on Gen Z-enabled memory support over time. The chart at the upper right depicts the full duplex aggregate bandwidth in gigabytes per second for several different Gen Z configurations of varying numbers of lane pairs and lane data rates, where a lane pair consists of one transmit plus one receive lane. We will consider two scenarios that represent how Gen Z may be introduced in a typical server deployment. Initially, Gen Z will not be integrated into the CPU, but will use an external bridge that provides connectivity between the CPU's high-performance interprocessor and/or cache-coherent links and the Gen Z links to the rest of the system. A typical bridge configuration would have 32 Gen Z lane pairs and supports either 25, 32, 56, or 112 gigatransfers per second data rates, depending on the generation of technology and target markets and workloads. The bandwidths that can be achieved with this solution are illustrated by the four leftmost bars in the chart. These bandwidth numbers are impressive when compared to 8 DDR5 memory channels operating at 4,400 megatransfers per second that yield about 282 gigabytes per second of bandwidth. The Gen Z links can support not only byte addressable memory, but block access storage, I/O to accelerators or gateways, and messaging to other servers through external Gen Z fabrics of a variety of topologies. Note that we did not include Gen Z attached DRAM in this diagram, as the latency through the bridge may be a bit too high for DRAM access requirements that would enable Gen Z attached DRAM to be the CPU's primary memory and allow us to eliminate DDR attached DRAM on the CPU. However, DRAM deployments that utilize flashback DRAM for persistent memory storage would be an excellent application for DRAM connected to the CPU via a bridge. Persistent memory and storage class memory will be more common as byte addressable memory when using external bridges to enable Gen Z connectivity for existing CPUs. Also, note that from the figure that if the solution requires more than 32 lanes, adding external Gen Z switches to expand connectivity will be common. Over the course of time, CPUs and other SoCs will integrate the Gen Z logic to provide native Gen Z link support. Watch the animation to see how this integration transforms, simplifies, and expands the Gen Z connectivity of a CPU. Now the number of Gen Z lane pairs that the CPU supports can double or more. We demonstrate this by using 64 lane pairs for a typical CPU configuration, which corresponds to the rightmost bars in the bandwidth chart. Future CPUs and SoCs may even support more than 64 Gen Z lane pairs, especially if Gen Z is used to host DRAM as opposed to using DDR channels. And speaking of DRAM, the integrated Gen Z interfaces on the CPU will now make Gen Z attached DRAM a reality, as latency will now be acceptable for DRAM media. In fact, Gen Z attached DRAM can even reside on external Gen Z switches connected to the CPU for further memory expansion, as the latency of Gen Z switches are only tens of nanoseconds. As Gen Z is integrated into host components like CPUs, GPUs, SoCs, FPGAs, etc., Gen Z offers many economic as well as high-performance benefits. Gen Z's adoption of leading industry standard high-performance serial physical layer leverages high-volume silicon libraries, which in themselves drives lower cost. In addition, using this technology enables Gen Z components to benefit from levels of pin efficiency not found in today's components, making them smaller, easier to manufacture, and lower cost. This also leads to printed circuit boards that these components are mounted on to be easier to design and manufacture, further reducing costs. Look at the figure on the left. This is a state-of-the-art CPU, GPU, or SoC with 8 DDR memory channels and upwards of 64 or more PCI lanes. You're looking at a device that has well over 4,000 pins. 50% of those pins are just for the DDR memory channels, including power, ground, control, and data pins. The figure in the middle illustrates the pin efficiency of DDR5 memory channels versus Gen Z interfaces at numerous data rates. Pin efficiency is the bandwidth of the interface divided by the total number of pins instantiating that interface. The pin density of DDR5 channel at 4400 megatransfers per second is about 0.55 gigabytes per second per pin, while the pin efficiency of Gen Z at 32, 56, and 112 gigatransfers per second is 4, 7, and 14 gigabytes per second per pin, respectively. Obviously, a significant improvement. What this allows us to do is build new CPUs, GPUs, and SoCs with 4x to 8x the bandwidth with 50% fewer pins dedicated to memory. This is illustrated in the figure on the right. This allows us to lower the device package costs and dramatically simplify the PCB design and lower overall system costs. Gen Z enables the ability to place DRAM or storage class memory on a fabric of arbitrary size and topology to be shared by other devices on the same fabric. Today, memory modules, whether they are DRAM or storage class memory, are captive on the local server that they are installed in. If workloads need more memory, you can add only so much memory to a server before you need to add more servers as shown in the figure above. Furthermore, to share the contents of the memory between servers requires relatively heavy protocols like remote direct memory access between the servers. These protocols and their associated memory transfers must pass through the processors, which have the memory and PCI root port controller logic. All of these bus and protocol translations reduce bandwidth and increase latency to access this memory remotely. Finally, as more and more remote accesses to memory occur, this traffic begins to affect the bandwidth and latency of local memory accesses from the CPU cores, thus reducing local CPU utilization. Gen Z is a memory semantic protocol that enables fabric-attached memory that can be added, removed, and provisioned independently of the compute components on the same fabric. And it enables direct access to memory from any component on the fabric without having to go through an intermediate processor. Therefore, GPUs, FPGAs, DSPs, etc. can have direct access to memory as well without having to go through both the PCI bus and the CPU and all of its internal logic to get to shared memory. So Gen Z enables GPUs, DSPs, FPGAs, custom ASIC accelerators, and etc. to be equal citizens on the fabric with CPUs as far as memory and data accesses are concerned. In addition, Gen Z enables CPU load store byte addressable accesses to memory, which are much more lightweight than RDMA protocols used today. Gen Z enable fabric-attached memory supports a variety of memory sharing schemes, including memory module leasing, where an entire module is owned by one compute component at any one time. Ownership can change as workloads require. Memory region leasing. Memory regions within a memory module are owned by one compute component at a time, and ownership can change as workloads require. Multiple compute components can utilize the memory in a module at the same time, but not share the same regions within that module at the same time. Finally, full memory region sharing. Memory regions within the memory modules can be allocated to more than one processor or compute element at the same time to facilitate collaborative workloads and scale-out deployments. In all of the above cases, software-defined management provides memory resource provisioning services. Gen Z enables fabric-attached memory on a wide variety of fabric topologies. Example topologies illustrated at the bottom of the slide include mesh on the left, traditional switch fabric in the center, and a two-tier fabric that could be spine leaf, clo, etc. on the right. The topologies used in a deployment can be specified based on the requirements of the target markets and workloads for the solution. Gen Z enables enhanced memory-centric or data-centric computing, where data can be directly sourced and manipulated in the fabric-attached memory by threads of execution running on one or more compute components simultaneously. This capability significantly reduces data movement to improve performance, reduce power consumption, reduce capital and operational costs, and enables infrastructure to achieve faster time to business-critical answers. If we'll be accessing memory resources over a simple point-to-point interconnect or over a complex fabric at distance over any type of cabling systems, we need to be able to provide rock-solid reliability to ensure no single points of failure, and the ability to support adds, moves, and upgrades to the fabric without disruption of basic load store accesses. Reliability, availability, and serviceability are key capabilities integrated into Gen Z technology. Let's look at a few examples of these capabilities. Gen Z's multi-link feature enables multiple Gen Z links to be connected between any two components. The figure on the top left demonstrates traffic flow if all four links are working properly between a CPU and a memory component, for example. The integrated Gen Z logic within the components distribute the memory transactions across the links, load balancing the traffic according to policies established by fabric management. This animated figure on the bottom left illustrates the case of a link failure. Let's say one of the links goes down between the two components. The components will automatically load balance the traffic that would have normally transited the broken orange link and redistribute this traffic over the remaining operational links. Once the orange link is restored, the Gen Z hardware automatically rebalances the traffic across all links. Gen Z's multipath feature is similar to multi-link, but applies to an arbitrary path through a switched Gen Z fabric of any topology. The figure at the upper middle illustrates one or more links are connected to one switch and one or more links connected to other switches. Now there are multiple paths between the components over which traffic traverses different switches. The animated figure on the top middle of the page demonstrates traffic flow if all the links and switches are working properly between two components that are connected through two links, one through each of two switches. The integrated Gen Z logic within the components distribute the memory and I/O transactions across these links, load balancing the traffic according to policies established by fabric management. The animated figure in the bottom middle of the page illustrates the case of a switch component or link failure. Let's say one of the switches goes down. The components will automatically load balance the traffic that would have normally transited the broken switch path at the bottom and redistribute this traffic over the remaining operational path at the top. Once the bottom switch is restored, the Gen Z hardware automatically rebalances the traffic across all paths. Gen Z daisy chain feature is an extension of the lowest latency point-to-point mode of operation of Gen Z. Gen Z supports the ability to daisy chain point-to-point connected components, as illustrated in the figure at the upper right. Daisy chains are useful topologies if we have a CPU that has a limited number of Gen Z interfaces. Instead of using external switches for expansion, we can daisy chain multiple components like memory to provide higher capacity while sharing the bandwidth of the links from the CPU. This is an ideal configuration for higher latency storage class memory. Daisy chains can be redundantly connected by having both ends of the chain connected to the SoC or CPU. The figure on the top right illustrates traffic flow if all links are working properly between the SoC and a couple of memory components configured in a double-ended daisy chain. The integrated Gen Z logic within the components distribute the memory and I/O transactions across the links, load balancing the traffic according to policies established by the fabric management. In this case, these policies would tend to favor the links with the lowest number of hops to get to the target's component. The figure on the bottom right illustrates the case of a link failure. The components will automatically reroute the traffic that would have normally transited the broken link via paths that use more than one hop through intermediate memory components to reach the destination component. Once the link is restored, the Gen Z hardware automatically reroutes the traffic in an optimal manner based on the original traffic management policies. In all of these configurations, these load balancing, failover, rerouting, failback operations are performed completely in the Gen Z hardware and do not require operating system software or drivers to provide this functionality. Gen Z's multi-link, multipath, and daisy chain features enable levels of reliability not seen in memory interconnects available today. More information about Gen Z's reliability features can be found in a video tutorial entitled The Gen Z Tenets, as well as from the Gen Z core specification publicly available from the Gen Z Consortium website. With Gen Z, we can place a variety of memory and compute components on a common fabric. The data stored in fabric-attached memory will be operated on by multiple compute components by multiple workloads in a multi-tenant manner. The data stored in the fabric-attached memory needs to be protected with rock-solid security to prevent inadvertent or malicious access to data in these memory components, or even a specific region of a memory component by unauthorized applications or workloads. Gen Z offers many different security and partitioning capabilities, but we will discuss a small number of them here. Gen Z access keys facilitate logically partitioning a fabric where each link can be associated with one or more access keys. One can think of access keys as similar to virtual LANs or VLANs in networking. The figure on the left illustrates a simple example of the use of access keys. Access key protection is enforced in Gen Z switches, either those integrated in any component or standalone Gen Z switches. When the component sends a Gen Z packet, it can include an optional access key in the header. When Gen Z switch forwards a packet with an access key field, it validates that the destination link has been configured with the same key. If not, the packet is dropped by the switch, an access violation audit log entry is created, and a security event is reported to fabric management by in-band or out-of-band management. Gen Z memory region keys are designed to protect components that share their memory resources on a Gen Z fabric. Typical components that share their memory will do so by sharing multiple memory regions to different compute components on the fabric. Memory region keys ensure proper partitioning and protection to prevent components from unauthorized access to memory regions shared on one or more fabrics. The figure in the middle illustrates a simple example of the use of memory region keys. When a component sends a Gen Z packet, it can include an optional memory region key in the header. When a component that is sharing one or more memory region receives the packet, it validates that the targeted memory region is protected by the same key present in the packet header. If not, the packet is dropped, an access violation audit log entry is created, and a security event is reported to fabric management by an in-band or out-of-band management. Notice that in the case of memory region keys, the validation is performed by the component that owns the memory resources versus the Gen Z switches that enforce access key violations and restrictions. Gen Z provides cryptographic security capabilities for authentication. Components requiring authenticated communication will share a secret key called a transaction integrity key, also known as a TIC, T-I-K. The TICs, which are relatively large keys, for example 256 bits, are distributed to the components in a secure manner using industry-standard key wrapping techniques by in- or out-of-band management mechanisms. The figure on the right illustrates a simple example of the use of cryptographic authentication. When a Gen Z packet is generated and sent, each component uses the appropriate tick and the Gen Z packet contents to calculate a secure hash-based message authentication code, or HMAC, that is inserted into the optional header in the packet. When the packet is received, the destination component calculates the HMAC from its tick and the Gen Z packet contents. If the HMACs do not match, the packet is discarded, an access violation audit log entry is created, and the security event is reported to Fabric Management by in or out-of-band management. In all cases, security events issued by components enables Fabric Management to quickly identify the issue and determine whether it was an inadvertent configuration error or a malicious attempt to try and access the target component. Again, these are just a sample of Gen Z security features that enable levels of security not seen in memory interconnects available today. More information about Gen Z security features can be found in the video tutorial entitled The Gen Z Tenants, as well as from the Gen Z core specification publicly available from the Gen Z Consortium website. Gen Z also provides a memory interleave feature that can be used to provide additional performance when accessing memory across a Gen Z fabric. The concept of interleaving is commonly used today in modern memory controllers that stripe accesses to consecutive regions of memory across multiple DDR memory channels and/or DIMM modules. Likewise, in storage systems, striping data blocks across multiple disk drives in a RAID 0 manner is also used to improve performance. Gen Z includes the specification of memory interleaving capabilities such that regions of memory space are interleaved across any number of memory modules and Gen Z fabric links and paths. The interleaving functionality is part of the Gen Z memory management function specified as the requester ZMMU, or memory management unit. The Gen Z core specification currently specifies two interleave granularities, 64-byte and 256-byte. The figure to the left is an example of a CPU that implements Gen Z host-based memory interleaving, and it has three point-to-point Gen Z links, one each to the DRAM media controller in three different DRAM modules. The DRAM modules have three memory regions defined: red, green, and blue. The requester ZMMU within the CPU has been configured to interleave or stripe memory accesses for particular host-based memory region to the three equal-size blue memory regions within the memory modules. Now, one or more memory requests are generated by the CPU. The ZMMU within the CPU will subdivide the requests into Gen Z requests based on the interleave granularity. In this case, the internal memory request is subdivided into 6 Gen Z read-write requests, and the first and the fourth are sent to the top memory module. The second and the fifth are sent to the middle memory module, and the third and the sixth are sent to the bottom memory module. Note, the operation of the CPU and its internal Gen Z requester ZMMU would be identical if there was an external switch between the CPU and the memory modules. Host-based interleaving works regardless of the external Gen Z fabric topology. The figure to the right demonstrates an example of Gen Z router-based memory interleaving. The Gen Z core specification defines transparent routers, or TRs, as components that can present logical memory resources on one side of the component while utilizing physical components on the other side as resources to substantiate the logical resources. Think of this as a memory semantic equivalent to a storage array controller on a storage area network. On the front side, logical storage volumes are presented to the servers, and on the back end, physical disk drives are used for the backing storage for the logical volumes presented on the front side. Transparent routers facilitate the ability to perform rich data services on the Gen Z fabric while hiding the complexities of the back-end Gen Z subnets, fabric topology, and physical components from the components on the front side of the transparent router. In the figure on the right, a CPU is connected to a Gen Z fabric. here instantiated as a single external Gen Z switch, to which is also attached a transparent router presenting and sharing a logical green memory region. The transparent router is directly connected to 3 memory modules on the backside, point-to-point Gen Z interconnects, and the TR uses the green memory region in each memory module to provide the backing storage memory for the logical green memory region. The transparent router is configured to accept received memory requests to its logical memory region and segment and interleave a series of requests to the back-end memory modules. In our example, the CPU sends a memory request to the transparent router targeting the logical green memory region. The transparent router then creates a series of Gen Z requests based on the interleaving configuration and sends these to the back-end memory devices. For read requests, the resulting responses are gathered together by the TR and sent back to the CPU. The interleaving between the transparent router and the memory devices are similar to those given in the host-based interleaving example. So interleaving is another example of how Gen Z provides high-performance memory access solutions for next-generation infrastructure. We have to take IT customers and operators on a journey from legacy infrastructure to next-generation infrastructure possible with Gen Z technology. This includes the ability for Gen Z infrastructure to support existing operating systems with no modifications, except for perhaps new drivers. Let's look at how Gen Z-enabled storage class memory is supported under unmodified operating systems. Operating systems have been adding support for direct access to persistent memory over the past couple of years, primarily to support emerging non-volatile DIMMs, or NVDIMM technology. The recently developed persistent memory-enabled file systems with direct access APIs between the applications and the persistent memory-enabled file system allow directly access file data in a byte addressable manner from applications using CPU load store instructions by mapping the file data into the application's memory space. The persistent memory-enabled file system is designed to work hand-in-hand with a block driver for the persistent memory so that the traditional block storage API and applications can also access the data in the memory devices. So here's the really cool part. Gen Z-enabled storage class memory can completely leverage this entire stack of software to enable both traditional block storage and new persistent memory-enabled file system with direct access APIs and their applications with absolutely no changes to the operating system or software stack. Even the existing NVDIMM driver can be used because Gen Z-enabled system firmware, the BIOS, will discover Gen Z memory resources and populate the ACPI tables to enable the NVDIMM driver to locate this memory. As seen in the animated figure on the right, the software stack is identical for legacy NVDIMM hardware or Gen Z fabric attached memory. The transition from NVDIMM technology of today to the storage class topologies of tomorrow are shown in the animated figure on the bottom left. Notice that Gen Z not only enables direct attached storage class memory on a CPU, but we can also support fabric attached storage class memory that has been provisioned by fabric management and memory resource managers for use by the CPU as shown. Let's take a closer look at the persistent memory-enabled file systems and their use with Gen Z storage class memory to see why this is a powerful solution relative to accessing storage class memory as a traditional block storage device. The animated figure on the right demonstrates the stark difference in performance of block storage under a traditional storage software stack and the storage class memory under the persistent memory-enabled file system with the direct access API. Let's say our application wants to access a couple of bytes in a certain offset in a file that hasn't been prefetched into a buffer cache. In the case of a traditional storage software stack on the left, The access request initiates the execution of anywhere from several thousand to up to 25,000 instructions on the CPU, while initiating up to a total of 5 different data copies in the different layers of the stack. The same request initiated through a persistent memory-enabled file system with the Direct Access API initiates an execution of 3 instructions on the CPU with no data copies to read or write a small number of bytes directly from the storage class memory. And oh, by the way, we didn't make the timing of this slide to scale because we'd have to wait all day long for the traditional storage stack to complete the request relative to the persistent memory file Direct Access API. So Gen Z enables low latency data access to storage class memory deployed in a variety of flexible topology options while using operating system software proven for use with today's NVDIMM technology. Gen Z's flexibility is evident in its support of a variety of topologies and scales of deployment. Gen Z's flexible physical layer options and capabilities enable Gen Z to scale from a simple component-to-component interconnect to a local system all the way to rack or row scale deployments. The figures on this page illustrate the various scales of memory deployment that Gen Z enables. The figure at the bottom left is an example of a server motherboard that has CPUs that connect to DRAM or storage class memory using Gen Z point-to-point or daisy chain topologies. This configuration utilizes low-cost copper interconnects and can employ either PCIe or IEEE 802.3 physical layer technologies. In either case, Gen Z enables flexibility in the placement of memory as seen here. DRAM and storage class memory can be placed anywhere on the motherboard, and it's not restricted to being placed near the CPUs where space and thermal issues abound. New custom form factors can be employed for new innovative solutions like high-capacity memory modules. Motherboards can also use switch topologies for memory expansion, similar to PCIe switches providing I/O expansion. The figure at the upper left is an example of a traditional server and a 2U chassis. This deployment model can utilize the same physical layers and topologies that our motherboard does, but now we can place DRAM and storage class memory modules in the same locations that small or large form factor disk drives, or SSDs, can be placed today. In addition, new custom form factors are possible, like large form factor DRAM or storage class memory bays and their modules that again fit where one would typically find storage drives today. These modules can also support hot plug capability to enable fast replacement of failed components. The figure on the right is an example of a rack scale deployment using Gen Z with a traditional topology of redundant external Gen Z switches at the top of the rack or in the rear of modular enclosures as shown. However, the mechanical structure presented is anything but traditional in that the rack of universal slots is used to host CPU, GPU, FPGA, DRAM, storage class memory, or any other type of Gen Z enabled modules. The Gen Z interconnects can be copper or optical and will be based on the IEEE 802.3 physical layer technology to span the rack scale interconnect distances. This configuration supports a variety of other topologies like torus 2D, 3D, spine leaf, CLO, etc. This example represents a level of composability designed for the era of memory-centric or data-centric computing of the future. This is the end of our use case discussion. We'd like to invite viewers to watch the other use case episodes of this series that discuss developing Gen Z-enabled components and systems. These episodes include low latency messaging use case, a logical PCI device or LPD use case, a compatible Ethernet messaging use case, block storage use cases, and data-centric computing use case. We hope you enjoyed this episode of the Gen Z tutorial video series, and thank you for joining us.